Hello, welcome to a new Cube video. My name is Pavel Starenko, and today I show you how to use bookmarks in the CubeGUI. Let's go.
So we are back to our terminal. We start our cube. We select our example cube file, get our start screen, and today we would like to learn a little bit about bookmark functionality. Bookmark functionality does exactly what it says. It marks, in the case of books, it marks the page where a reader stopped to read and would like to return to it later on. In the case of cube, that marks a state of our trees, the selection state, the expanding state, and so on of our cube GUI, so that one can return later to the state and proceed with the work. Where do we find this bookmark functionality, our bookmarks? So if one takes a look at the menu display, one sees down here, show bookmark toolbar. In our case, it is already visible. If it is not marked, one just clicks on it and it appears. So that is this our toolbar, and it has three buttons: load bookmarks, save bookmarks, and edit bookmarks. So the save bookmark would be basically create the bookmark, create or save current state. The load bookmark, if you click on it, you will get a window. The window where one can select some named, obviously, bookmark, and to every bookmark there is description which one can add as a side note. So we have no bookmarks saved so far, so there is empty. If we go to edit bookmark, it's pretty much the same window, just there is a ability to remove some bookmark which one doesn't need anymore. We have no bookmarks, so nothing to delete. Okay, let's take a look how it works. So this is a typical example of performance profile. How one makes actually performance analysis. I would rather advise you to take a look at our tutorials in Virtual Institute High Productivity Supercomputing, or at another tutorial videos in our partner channel, Pop HPC. There one gets better insights what every metric means and what all those values means. In this video we will just expand some trees and without going into the actual deep meaning of every value. So let's take a look at the call tree, for example. So we have the application. It has some subcalls, and in this case we see that majority of time this application spends in ID call. That would be our first choice for optimization, for example. If we take another look, we see that there is a verify, for example, there is a setup MPI, initialize, exact RHAs. These calls would be our second choice for optimization, just as a side note. So if we take a closer look at ADI, expand it, we see that the execution time, we're talking about time because we have selected time metric. So execution time is distributed here nearly equally between copy phases, xsolve, ysolve, and zsolve, and a little bit of add. So these calls are obviously our calls of interest. If we take a look at copy phases, closer look, so for example we expand it and we see that it has subcalls MPI receive, isend, byte all, and compute RCS, and majority of time spent again in this compute RCS. If we expand here verify, and we see that there is also copy phases. So if we expand it, we see that it has very same structure of subtree, so that there is a suspicion that that might belong to very same region in our source code. So this we can take a look if we click on a context menu and we select this info menu. The details about this window I will explain in another video. Here for us is only interesting this line. So the source file of this call is copy faces F Fortran, and if we select it here, we see that very same file. So obviously that is very same region, and it means that if we optimize copy faces, not only this execution, not only ADI gets experience optimization, but also verify. Here, if we collapse this copy faces, we see that execution time here is approximately 5,500 seconds. Here is 22 seconds. So one can have suspicion that maybe execution in this call path goes different way and takes longer than if it is in verify. So if we take a closer look on every rank, so we see that copy faces in ADI call takes approximately 87 seconds. And if we take a look at number of visits, for that we have to select metric visits and take a look actually at exclusive value. That would be 251 call of copy faces. So, and if we divide this value 87 seconds by 251, we obtain approximately 0.35 seconds. That would be the ratio of every individual execution of copy faces. And if we take a look at here, so we can take a look at the copy faces. The time is 0.35, and if we look at our exclusive visits, we see that's only one visit, and it looks like it has the same execution time like in ADI. So probably the same has the same execution path like in case of ADI. So this, for example, is maybe interesting finding, and one would like to record it, to write it down, so that one returns to it later on and can maybe proceed with this finding. So let's see. Let's take. Let's mark this calls, and we can actually create our bookmark. For example, region copy faces. And we write our findings. Same source code and approximate individual execution approximately 0.3 seconds, 3.5 seconds, and different times of visits. Let's say that's our findings, and we save them under the bookmark region copy faces. Okay, so this we marked. Actually, the calculation which we just did by dividing the inclusive time of copy faces over exclusive time over visits can be done also within a CubeGUI using so-called technique, derived metrics technique. But how one uses it within the CubeGUI using the plugin metric editor, I will explain in another video a little bit later. And the whole feature of derived metrics within a CubeLib I will explain also in one separate video. Stay tuned. Then let's keep looking. So for example, we have here xsolve, ysolve, zsolve. If we expand them, we also see that they have similar structure. So the majority of time spent in xsolve cell. If we expand it again, we see that the time is actually in exclusive time, which means that the majority of time spent in a not instrumented part of this call. So the same is valid for these calls as well. Then if we take a look at metrics, for example, if we select the critical path, go here, and we see that the highest values are again exclusive values of X solve cell, Y solve cell, and Z solve cell, and also this compute RCS and copy phases. So knowing that these values are from critical paths, we see that these calls are best, or actually first candidates for optimization, as we know that the regions which contribute to critical paths, they actually contribute also to the total runtime. If one tries to optimize something, some region which is not on critical path, one actually increases just waiting times, but one doesn't shorten the runtime of the whole application. But that's just side note. So let's say that is our finding, and we would like to mark it again as a second finding. So regions for optimization, and we make maybe as a finding contribute to critical paths, and the best candidates for optimization. That is probably our note for this finding. So maybe if we keep working on it, we will find, of course, something else. So anyway, let's pretend that we stopped to work with this cube file. We closed this experiment, and we actually closed the cube, and we stopped to work on it, and maybe went for holidays. Anyway, later on we return to this performance analysis, and we would like to take again look at this performance data. So our cube opens in this state, and we have to actually recreate our whole logic, and we probably already forgot what we were thinking about, so what to do. But fortunately we have our bookmarks, so we can open the dialog and see, we have here two bookmarks. So one bookmark is copy phases, and here are findings at the same source code, individual execution 350 milliseconds, and different times are due to different number of visits. No good. So let's take a look. It opens the call tree and recreates the state with which we actually let's say made this node. So okay, we know that copy phases belongs to the same region, and the numbers are due to different different execution. Okay, so what is about the second our bookmark? We take a look. Region for optimization, and we see that they contribute to critical path and best for optimization. Oh, that's interesting. Let's take a look, and we see that the cube jumps selects the critical path metric and selects these regions, so that we see already, these regions, they contribute to our critical path. So that is exactly for what this bookmark functionality has been introduced. Another scenario, besides of user versus future user, is the client analyst, like we do it, for example, in our partner channel in Pop HPC, where the client provides the source code or application, and performance analysis actually performed by the analyst. So in this scenario, analyst is working on performance data on a cube file, for example, and does exactly what I did, makes a notes, and store findings during the performance analysis, and by the end of the work the analyst provides a report to the client. So next to the report, the analyst can provide also a file with all these bookmarks, which is in our case is located in very same directory where the cube file is located. So in our case it is in shared doc CubeGUI examples, and if we take a look, we see that there is a trace cube x, that is the file with which we have been working, and we have this trace ini. So analyst can provide this file to the client next to the together with a performance report, and the client can while reading report can recreate all these findings or states with which analyst made one or another conclusion. So that simplifies understanding of the performance report between analyst and the client. So that is actually the main reason why this feature has been introduced, and I hope you understand more or less how that works. I hope you like this video. Subscribe, comment, and give us a like. Thank you very much, and see you next time.